System reliability, learning objectives of this lesson is listed in here. At the end, you will have a familiarity with probability and understand how they apply to reliability theory. Understand the mathematical definition and meaning of failure rate, reliability, and mean time to failure. F, mean time between failures. F, mean time to repair. R. You will understand how to determine the reliability of a component and understand how to determine the reliability of different system configurations. Okay, we so far have focused on the design and stage of design. At the end, we'll have a design, and the success of the design is usually considered in terms of functionality, how the design meets the functional requirements of the customer. But actually, there are some other issues that might be considered in the scope of the design, the success of the design. These are reliability, safety, and maintainability. These are rather related to the life of the design after it's operated by the user. But as engineers, we have to somehow consider these factors in the design stage. Okay, let's have a look at reliability. That is a review, and we can first define some basic terms: experiment, event space, probability. You may imagine that you got a system, let's say an aircraft, and you are given some parts of the aircraft, and you do experiments. You test some parts. You measure, for example, voltage values or current values. Each measurement here, the process of measuring a quantity, is simply an experiment. And the outcome of an experiment, so particular voltage level that we measured, so once we conduct an experiment, is going to be an event. And if we consider all possible outcomes of the measurement, we simply form our event space. And probability is a measure of how likely one of or more of these events occur. From probability course, I'm sure that you are familiar with six-sided die experiments. When we roll a six-sided die, we might get 1 to 6, 1, 2, 3, 4, 6. So this set forms the event space. So the outcome of this experiment should be one of this. And any of this is going to be an event. Let's say I rolling. We've got 2, so that's an event. Probability is about how likely this event occurs, and apparently, if we consider EI is 2, that's going to be 1 over 6. We have some axioms for probability. Probability value should be at least 0 and greater than 0. A number between 0 to 1, and the probability of event space is 1. It cannot be a negative number. So let's look at next random variables. Random variable is defined the outcome of an experiment that has a continuum of possible values. And we usually use two functions regarding random variables. Probability density function, PDF, cumulative distribution function, PDF. PDF has a counterpart in discrete form of the mass function or PMF. Usually, we use small p sub capital X of X to denote PDF. In some textbooks, that is simply small f of X. Here, capital X denotes our random variable. Small x represents the values of this random. Cumulative distribution function, on the other hand, denoted by capital P sub capital X of X or capital F of X. Probability of a number or value of a random variable X in between A to B can be then written in terms of probability density function. Actually, almost all probabilistic values can be calculated by using either PDF or CDF. Then the problem is usually to form this PDF and CDF. Once we got PDF and CDF for a particular variable, then we can proceed and determine all other values. There are two parameters that can be derived from PDF and CDF are mean value and variance or standard deviation. Variance is part of standard deviation. At the bottom here, you can see mu as the mean, which is simply integration of PDF times X from minus infinity to plus infinity with respect to X. For variance, it is X minus mu squared times PDF from minus infinity to plus infinity with respect to X. We can also derive some higher order statistics, higher order parameters to analyze the particle. Okay, as we said earlier, PDF and CDF are not easy to form for a particular experiment. So we usually have some models, some PDF or random variable density models. We mostly in practice try to fit our experimental work, try to fit it into one of those models. One of these models is the most important. One is Gaussian random variable or normal variable. As we can understand from the name, normal comes from the fact that this is very common in our life, such that that is normal. Okay, its PDF is shown in here. It's a curve, as you can see, whose center is mean value, and its width, the width of this curve is dependent on standard deviation or variance. Higher the standard deviation, more wider curve. Lower the standard deviation, steeper curve. Mathematically, this can be written on the right-hand side. And its CDF can be derived from the PDF, which is particle value X, and we simply integrate Y minus X. CDF is usually here used, usually defined in terms of spatial error function, which is denoted by phi of X. And at the bottom, you can see on the right hand side That's a monotonically increasing function, start 0 to 1. So the minimum value of CDF is 0, the maximum value is 1. It increases monotonically. Another random variable that we come across is uniform random variable, where we have here rectangle PDF is defined P and probability that X as a value in between this is simply 1 over P minus A. We have also exponential random variable. It's simply an exponential function. Okay, now let's come to reliability. Reliability is simply it's the probability that a device is functioning properly at time t, so has not failed. To understand reliability, we have to take a closer look into the failure, and we define failure rate. It's denoted by lambda of t, the expected number of failures per unit time. We usually operate a batch of devices for a given time interval and then count how many of these devices fail during this time interval. So it's somehow a time-consuming process. We need time to do it. And when we look at the devices, at the bottom you can see the failure rate with the time. We have 3 phases here. The first one is burn-in phase, where we have relatively higher failure rates. See, that's due to the fact that there may be many defects when we type the device and try first time. So failure rate is higher when we start, and it decreases slowly. And at some point here, the failure rate becomes constant. Then it continues for a very long time. This phase is called service lifetime. We usually, as we said, determine this large number. Usually have a failure rate of such values in here. 1 failure out of 1 million hours, 1 million hours. See? Now, after a service lifetime, we see that there are 2 curves here. One is mechanical, one is for mechanical devices where failure rate increases again, just like the burning phase increases, while it's still constant for electrical devices. That's due to the fact that for mechanical devices we have some wear out, frictions, or affects the life of mechanical, limited comparison with electrical. So that's why we have. So there's always a lifetime for mechanical devices, but for electric devices, this is longer than. So let's see the mathematical basis of failure rate and probability. Let's assume that the failure rate PDF has PF sub P, capital P of P. Then the probability that a device fails between 1 to 2 is going to be the integration of PDF of failure rate. And this corresponds to CDF of failure rate at T2 minus CDF of failure. Then probability the device fails by the time T can be derived as 1 minus R of T. So simply failure and reliability are inversely proportional. It's just like flipping a coin. When we flip a coin, the probability of having head and tail is 1/2, and if one increases, the other decreases in proportion. So then if we try to plot the failure and reliability, we see that reliability 1 and then decreases slowly to 0, while failure 0 increases slowly, then reaches unity. So both are probability and they intersect on which is 1/2. So higher the reliability, lower the failure. Higher the failure, lower the probability. So there is a derivation, some page in the textbook or in another material. You can see how to relate failure rate. Here we are not going to derive, but use them. Lambda of T, the failure rate, is empirically determined. The PDF can be written as R of T, the reliability times failure rate. So R of T can be written in terms of failure rate as an exponential function. After eliminating PDF from this equation for a constant failure rate during lifetime, reliability can be expressed in terms of an exponential function. It's dependent on the failure rate and time. Times T, and lambda here is constant. So simply, if you go back to the previous slide, we are working somewhere here. Okay, service lifetime. Here, there's an example, a transistor, for example, with a constant failure rate of 1 failure per 1 million hours. What's the probability that the transistor will be operable in 5 years? So simply reliability, 5 years is going to be exponential lambda T. Lambda is 1 per 1 million hours, so 1/10⁶ hours times T. The duration here is 5 years. So we have to convert 5 years into hours. 5 years times 305 times 24 times 60. No, not 60, 24. So we can estimate reliability. And what we see that at the end, this number should be something close to unity. If it is a reliable equipment, we should expect something close to unity, like 90% or 0.9, 0.8, 0.7. Mean time to failure, it's another parameter that we have to consider. It's simply on average, how long does it take for a device to fail? This is usually applicable to replaceable or non-repairable, replaceable or non-repairable. MTTF, mean time to failure, is simply the mean value of the failure rate. So from the mean value formula, we simply write f sub t of t times t from 0 to infinity with respect to. This gives us 1/λ if we take f of t as in previous slide. Then the reliability can be related to ft of t in terms of exponential function again. So now let's see the same example in previous slide. transistor with a constant 1 failure per 1 million hours. Now determine the MTTF and the reliability at the MTTF. So MTTF is a number, time, right? And we'd like to see the reliability at this time. First, MTTF is going to be 1 over lambda. So we simply take the inverse of this number. And then put it into here, time, and determine the reliability. MTBF and MTTR, these are not available in the text or materials, so I just produce those terms. These are aerospace industry. Mean time between failures. This could be applicable to repairable and replaceable, non-repairable devices or equipments. Simply total operational uptime between failures or number of failures. It's a very important parameter in many of the components, devices, or modules. You can see in the data sheet this parameter. Mean time to repair, this is rather about the operational aspect of failure. Suppose that we have a failed product and would like to see simply after failing how much time we need to have this product running. Okay, so simply as definition, how long it will take to get a failed product running again. So this is rather about the logistical issues, transportation, for example, service, equipment or staff. So then failure rate estimates. Here, as you might see, failure rate, lambda, is quite critical. So how to determine this lambda is quite a challenging problem. There are too many parameters, operating conditions, variations in power, voltage, temperature, all affect the failure rate of an electronic. So then people, especially collected data over the years, and then they develop a handbook, analyze those data, and this is quite popular in defense and aerospace industry. Once you work for defense, quite important use. Or here I'm giving an example, BJT reliability. Suppose that this BJT is used in a missile launcher. It has resistors together in operational conditions. Important here. So based on this handbook, mathematically, failure rate here is given as multiplication of 4, 6, and 7. Each represents a different physical effect that imposed on this BJT. The first one is about the temperature, for example. The high values in here each represent a different. We should look into the handbook and determine which values are applicable for this parameter, for this BJT. So at the end here, we got a failure rate of 1.59 and to do -1 divided by 1 million hours. So over 1 million hours, 1.50. Then we can determine mean time to failure, which is 1 over lambda. We see that that's 71, more than 71,000 years. So this BJT, on average, might continue working or providing service more than 71,000 years. So that's a very good number. So the reliability then can be estimated from this for 20 years. It's 0.9997. So BJT is highly reliable after 20 years. So this was a component that we have considered here. Suppose that we have a system with many subsystems or modules. So there are two cases here, two configurations here. Once we understand these two configurations, then we can apply this to any type of system configuration. Series system, series connected, redundant system, or parallel connected. Series system is a system in which the failure of a single component leads to failure of the overall system. And it's illustrated in here. Since they are connected in parallel, once one of these fails, then the system fails. For a redundant system, it contains multiple modules performing the same function, where a single module would be enough. You don't need to have all modules working together. For series system, or reliability, it can be written as the product of the reliability of each subsystem. So R1 of T, R2 of T, Rn of T. And R of T is here, again, e to the minus T, then the constant failure rate, lambda S, is going to be summation of failure rate of all components, and mean time to failure is going to be 1 over lambda S. Okay, so once we know the reliability of each subsystem, then we can estimate the overall reliability of the system. Parallel system or redundant system, this is quite common in aerospace or almost all equipments in aerospace systems firms are redundant. There are always two identical systems working together, and if one fails, the other still works. Here, to understand reliability, we start with failure function. Failure of the system is going to be multiplication of failure of all these systems. And then we know that the failure is 1 minus reliability. Then we can write the reliability for a parallel system or redundant system as this formula, 1 minus failure. So 1 minus that of 1 minus reliability of each subsystem. As we said earlier, in practice, almost all systems of this two, and here you can see one such a system. We have subsystem 1 and 2 connected in series, subsystem 3 and 4 connected in series, and this S1 and 2 is connected. Sorry, parallel. S1 and S2 are in parallel, S3 and S4 in parallel, and S1, S2, and S3 and S4 are connected in series. So then we can determine the reliability of the system, or if the overall reliability is given, we can estimate the reliability of any subsystem, subsystem pairs. Here, fixed time T, reliability of system 1 and 2 is 0.8, and system reliability is 0.9, then the reliability of the subsystem, so S3 and S4 together. We can determine reliability of system 1 and 2, this parallel conflict. which is 1 minus R1 times 1 minus R2, and the reliability of the pair of the system, 3 and 4, is 1 minus R3, 4 from here. And then the system reliability is multiplication of the reliability of these parallel systems. Then we can determine the reliability of the system 3 and 4. So for any type of system, then we can start from the very beginning, the component level from the handbook, filter handbook. We can estimate the failure rate of each component, and then simply make a series and parallel connection of overall system, and then estimate the reliability.